Hello, everyone. Welcome to mRNA Applications in Discovery and Development Digital Week. Brought to you by the organizers of the TIDES Conference Series, visiting Amsterdam this fall and Kyoto and Boston next year. My name is Mike Moriarty. I'll be your host for today's session titled Chromatography and mRNA Production from Analytics to Purification. First, I'll cover some quick housekeeping items. If you experience difficulties with audio or advancing slides, refresh your screen with F5. If you're experiencing other issues, hit the question mark button to receive assistance. At any time during the presentation, submit your questions into the Q&A window on the left-hand side of your screen. In 24 hours, you'll receive a link to watch the recording of the session. Let's now begin by introducing our speaker from Sartorius BIA Separations, Sekirnik, Head of Process Development, mRNA/pDNA. Thank you for joining us today, Rock. Now I'll hand it over to you to begin the presentation.
Thank you, Mike, and thanks to everybody for joining today. It's a great pleasure to be here. I need to correctly hit the screen share button, and assuming that I've done this correctly now, you should see my screen. And you should join me in being this scientist looking at mRNA production, mRNA being born through various tools. And it's a great passion and joy of mine to actually present how at Sartorius BIA Separations we think about the various uses of chromatography in an mRNA drug substance production process. And we don't really separate analytics from purification, but we try to combine them as much as possible. And in the next 45 minutes up to 50 minutes or so, I would like to give you a breakdown step by step through steps of mRNA process, how we speed up process development, how we optimize individual steps, starting all the way at the beginning, which is, of course, at production and purification of plasmid DNA. Before I begin, I would like to give a few words of introduction of who we are and where we come from. And depending on how you spin the globe, spin the wheel, of course, always in the center. So we are located in the center of Europe, in a country called Slovenia, bordering Italy, Austria, Croatia, and Hungary. And we're located in the site that you see here on the slide, where we, in fact, manufacture something called monolith chromatographic columns, CIM, and we also develop applications in the field of mRNA and plasmid DNA, which is what I oversee, as well as in gene therapy vectors like AAV, adenovirus. We also look at phages and other interesting large molecules. And always welcome visitors and partners. And part of the appeal is that we're located actually in a very fruitful wine valley, which makes it for a pleasant visit, but also provides us as process developers in the area of biopharmaceutics some inspiration, I would say. And we try to draw some inspiration from the way that the wine industry has been dealing with large volumes of bioactive ingredients for hundreds and hundreds of years. And now we're refining those tools to make plasmid DNA, to make mRNA, and so forth. So the star of the show today is, of course, mRNA, as also the lecture series is dedicated to. And I would like to say that in our hands, mRNA is a very interesting biomolecule, and we look at it in a relatively simplified way, I would say, which might also help us develop better processes. So we're not concerned with sequence optimization and with designing new sequences to target particular modalities. No, this is what our clients do. This is what our collaborators do. We are really focused and zoomed in on making sure that the sequence, their target sequence, is produced in high quantity and high quality and purified to the highest purity specs possible. And the way that we look at the mRNA molecule is in a threefold way, basically. First is the sequence is correct, of course, that the two key features, the 5' end, the cap is correct, and the 3' end is correct, so that it's polyadenylated. And those are, let's say, the sequence considerations that we're concerned with. But then we're more interested in the physical-chemical properties of mRNA. And there we are oftentimes surprised at how the field is, in fact, still surprised by the fact that mRNA is a huge, gigantic molecule. I think one of the largest biopharmaceutical molecules currently available on the market. So one of my favorite interview questions for a young scientist is to estimate the molecular size of a standard mRNA molecule, let's say of EGFP or of a spike protein encoding mRNA. And it's a tougher question than it first seems. Of course, we are in the megadalton territory, where monoclonal antibodies were in the 100,000 Dalton, 150,000 Dalton territory. So we're now nearly tenfold higher molecular weight, which brings with it various challenges for the process. Of course, also some benefits, because you can, on the basis of size, differentiate between mRNA and other molecules. And of course, this size issue or size property is even potentiated for larger RNA molecules like self-amplifying RNA, which is nearly an order of magnitude larger still. Apart from the size, what also characterizes mRNA, sets it apart from other biopharmaceuticals, is the charge. mRNA contains a very, very strong negative charge. I think stronger negative charge than most people appreciate. And we are in the very low units of pKa, and we have to take this into account when purifying it. mRNA, when in presence, either native, but even more so in presence of certain salts, also exhibits strong hydrophobic behavior, which again can be a challenge or a benefit depending on the purification approach and skill. But we like to make full use of the fact that mRNA exhibits different hydrophobicity depending on the sequence and certain properties. And finally, a feature that is inherent in the sequence makes mRNA very suitable towards affinity, purification, and analytics, and is the fact that for biological activity, mRNA and saRNA need to be polyadenylated, and the fact that we have this long chain of adenines means that we can use a complementary ligands immobilized onto chromatographic resins for affinity, purification of mRNA. So those are the four key features which are important for all of the subsequent work, which I will define. And most of what we'll talk about today is captured, in fact, in this slide. So if I start from the back, I would like to arrive at highly pure mRNA, and how we'll get there is we will describe the entire process of making mRNA from linear plasmids, DNA, through IVT reaction, through purification. I will not dwell too much on TFF infiltration. This is covered elsewhere by my colleagues from Sartorius. But I would like to actually spend more time than I usually spend on how to get towards a pure linear plasmid DNA. And I would like to touch upon certain steps in the plasmid production, because that's, I think, quite a pertinent question in the field of mRNA. I see more and more mRNA companies also internalizing plasmid production, and there are a lot of open questions about how to make pure plasmids that's suitable for production of mRNA. And so I dare to start the presentation by saying that production of mRNA drug substance actually starts with plasmid DNA and allow me, therefore, to spend a little bit of time on the plasmid itself. The technology of making plasmid is actually quite old, and still I think the biggest and the best plasmid processes are to a large extent based around technologies and techniques that were actually designed and derived and even optimized in the 70s and the 80s. Certainly alkaline lysis, which is actually one of the most challenging steps from the perspective of scale-up, is largely still based around the seminal paper by Birnbaum and Dolly from 1978, if I'm not mistaken. Little changed since then. Plasmid is a star but quiet raw ingredient not only for mRNA but also for AAVs, used for transfection of to produce AAVs, and also, of course, just as a naked vehicle, just simply plasmid vaccine. It exists, as you may know, in various isoforms: supercoiled, which is the one that's typically used for transfection; open circular isoform, which in fact is an impurity in most processes; and linear form, which in our case will be the target if we want to produce mRNA. And how do we produce it? Well, we produce it from E. coli fermentation. E. coli is engineered to produce plasmid of interest. We need to lyse E. coli to release the plasmid, and in the process of releasing the plasmid, of course, it releases all other host cell impurities as well, host cell proteins, host cell RNA, some genomic DNA. And so it's very important for us to keep track of our target, the plasmid, in amongst the sea or the ocean of impurities that are everything else that used to be E. coli cell. And here is the first point in this presentation where we meet chromatography, namely, it's our strong belief, and I think also somehow validated through practice, that to optimize and to understand a process of isolating plasmid, we want to keep an eye, we want to monitor plasmid quantity and purity from the very first unit operations in the process, namely ready lysis. Sometimes we can even look at plasmid concentration outside of a cell, of an intact cell. That is quite rarely done. It could be done even with chromatographic approaches. But the first point where we want to look at concentration of plasmid is typically post-lysis. And typically what we would see, although this is already a chromatogram taken from a couple of unit operations down, we would see plasmid, of course, in low concentration at the beginning of the process, together with some RNA impurities and proteins and other impurities that do not bind to a chromatographic column. This method will be taking forward with us throughout the next couple of steps as we purify out our plasmid. And I would like to say it's now becoming quite a generic and generalized HPLC analytical method based around anion exchange chromatographic column that gives us high resolution of plasmids, particularly supercoiled plasmid that's separated from open circular and linear forms, as well as actually being able to quantify residual RNA, which is a predominant impurity in the plasmid process. And it's one of our tenets in process development to actually use this as one chromatographic method to support purification chromatographic methods as we move throughout the process. So let's see how we use this to generate some useful data whilst producing plasmid DNA. Well, the first step, as I mentioned, in the process of isolating plasmid DNA is alkaline lysis. And there is, for example, the first question arises: what is the duration of lysis? What is the concentration of sodium hydroxide? and also what is the resuspension ratio. And we see a lot of variability when researchers perform these experiments throughout the world. They rely on very different analytical methods, a lot of them based on methods that produce a lot of interference from other impurities. And time and again, we see the benefit of actually applying a method that can resolve plasmid, as we see here. This is our supercoiled plasmid, away from RNA impurities and away from other proteinaceous impurities, to be able to give us quite accurate determination of plasmid content already in those earliest process steps, where the relative amount of plasmid is still very low. And so we can use this sort of analytical support to compare, for example, the impact of resuspension, volume of cells, to give us really the recovery ratio in milligrams of plasmid per gram of cells, dependent on the resuspension ratio, to, for example, impact of calcium chloride precipitation to remove RNA impurity. And the way that we see this on analytical chromatogram looks a little bit like this. So here we were increasing the concentration of calcium chloride, and we saw the plasmid getting nicely resolved away from RNA impurities. If we didn't add any calcium chloride, RNA impurity was so fully present that it actually obscured the plasmid. That's actually quite a rare case. We typically use at least half molar and sometimes higher concentration of calcium chloride, where we see RNA impurity significantly reduced and plasmid concentration here relatively increasing. Here I'm not, in this case, optimizing right now for anything. I'm giving an example of things that you can see relatively early on in the process. Very few other techniques are able to give you information about the concentration of plasmid so early on in the process and do so accurately. So mass balance calculations throughout the process are much, much more accurate. Then the next step in the process is first chromatographic purification, where we want to remove now this RNA impurity, which is in chemical terms the closest impurity to plasmid. We want to remove it chromatographically. And again, quite a well-validated approach is to use a weak anion exchanger, diethyl amino ligand immobilized on a monolith support under particular loading conditions, which already remove a lot of impurities like proteins in the flow-through fraction. And if we optimize our loading condition correctly, we can even remove already RNA at that point and differentiate based on conductivity between RNA and the plasmid, and then either in step or linear gradient elute the plasmid DNA in a relatively narrow elution peak, which means that we also concentrate down the plasmid typically to about 0.3, 0.4 milligram per milliliter. We have done this approach now for dozens and dozens of different plasmids, from small plasmids used for production of mRNA of, let's say, 3,000 to 6,000 kilobase pairs, all the way up to about 25,000 base pair plasmids, where we only have to adjust pore size of our chromatographic support to use a larger pores, due to the fact that 24,000 base pair plasmid is still a couple of, at least an order of magnitude larger than even the molecular sizes that I was talking about before. So this is quite a generic method that is very easily applied, I would say, and it's followed typically by a polishing step, depending on the end application for the plasmid. If the plasmid is used for transfection, then it's good to isolate it in high purity of supercoiled isoform. And so I want to give you here two approaches to doing so. We pretty much always opt for the use of hydrophobic interaction chromatography, or HIC, because that's got high resolution, particularly in monolith format between supercoiled and open circular isoforms. And here we also understand the behavior of supercoiled very well, in the sense that we've demonstrated time and again that no matter what the size of the plasmid is, we can pretty much always use the same concentrations of loading salt, which in case of HIC for the use for purification of plasmid is ammonium sulfate. And we now understand the concentration of ammonium sulfate so well that we can pretty much prescribe a generic concentration of ammonium sulfate for loading and then for elution of supercoiled plasmid. And I can actually say that this can be done in a way that any percent impurity of open circular or even genomic DNA impurities can be loaded on the column in such a way that only supercoiled isoform binds. Everything else is washed through the column in flow through, and upon elution we recover, I will say, to be very conservative, more than 95% pure supercoiled isoform. And I would like to impress upon you that this is now standard practice. We no longer have to be reaching for 85% purity as it used to be stipulated in the olden day purity. It's actually through a relatively generic purification procedure that we are now calling selective hydrophobic interaction chromatography, based on the fact that we can select for binding condition for supercoiled isoform, that we can really get very pure supercoiled plasmid out without any steps involved. We literally load the plasmid at a particular pre-selected ammonium sulfate concentration, which depends on the impurity profile of the load, and we elute with the lower concentration of ammonium sulfate. This is an example here shown either quantified by the same analytical chromatographic method as I used before, just this time we are dealing with a much purer analytes. So we resolve between supercoiled and open circular isoforms in the load. This was our load. As I said, we selected for loading conditions such that open circular does not bind to the column, whereas supercoiled does, and we do so up to the point of saturating the column with supercoiled DNA. At that point, when the column is saturated, and if we go all the way, we see this in a second increase, second breakthrough, we call it in the UV measurement. At that point, we elute and recover pretty much 100% pure supercoiled plasmid, verified by agarose gels, verified numerous times also by capillary electrophoresis. This methodology can be used to produce then linear plasmids or any other plasmid that may be of interest. There are many studies showing positive impact of highly purified supercoiled plasmid also on other transfection activities like producing AAVs and so forth. And the next step now we're moving slowly towards producing mRNA. We need to be linearizing our plasmid. I used the same, so I mentioned earlier that we'll be using a generic analytical anion exchange analytical HPLC method. This is the same method used now for the third purpose. If the first purpose was to optimize lysis, second was to optimize purification of supercoiled, and now the third use is to optimize linearization. If you're depending only on agarose gel electrophoresis, it might be difficult to sometimes decide at what point has this band for supercoiled or for open circular really vanished. So it can depend on the saturating the gel with light. But when you're when you perform a HPLC-based analysis, which gives you a UV-based readout, there can be no doubt. You can integrate areas under each peak and produce out of it, for example, this nice kinetic curve that looks at the kinetics of linearization. Yeah, and so we translate area under the curve of supercoiled isoform decreasing and linear isoform increasing with time, and we can plot this as area under the curves. And this is one approach towards monitoring or towards optimizing, for example, different conditions of linearization. You can add various reagents, like sometimes BSA was used for linearization. You may want to check what's the effect of taking BSA out. You can play with concentration of enzymes to try to decrease the amount of enzyme needed to fully linearize. You can play with temperature and so forth. Always it's best to have quantifiable data, and quantifiable data is best produced by HPLC analysis that depend on UV detection. So this is actually a summary of all of the workflow that goes into producing the key raw material for making mRNA, namely linearized plasmid. So I walked you very quickly through the steps, didn't touch upon the culture, but did mention the harvest, alkaline lysis, clarification, and then the capture step on the DEAE monolith. I added in there a C4 HLD, so HIC step. I mentioned it from the perspective of producing supercoiled plasmid. It can also be used then to purify out linearized plasmid in much the same way. And I can do that rapidly, and I can iterate through optimizations fast if my analytics can support me with rapid and quantifiable data. And I hope I showed you a few interesting examples where we can use relatively fast analytical methods based on HPLC, where runtime is typically around 15 minutes or so. That gives us very precise information on concentration of open circular, linear, supercoiled isoforms, and so forth. So now let's spend the remaining time on actually making mRNA out of this linearized plasmid. The key and most important, also most expensive unit operation or a process step used to produce mRNA is in vitro transcription reaction, IVT. And it's a multi-component reaction. It's quite a complex reaction, and yet at the bottom of it, it is not a biological process. It's in fact a chemical reaction. And I think as an industry, we would do well to think about it as such rather than a biological process, which it is not. It is a reaction that typically takes about 2 hours. We try to speed it up if possible. It requires plasmid we've just produced. It requires a polymerase, requires building blocks in the form of NTPs, sometimes capping reagent, always magnesium, sometimes pyrophosphatases to convert pyrophosphate into more soluble phosphate. Advisable is to use RNase inhibitor and some other additives to solubilize the nascent mRNA. 2 hours is much faster compared to a typical biological process, as was mentioned here in the recent white paper. In order to monitor and in order to optimize this relatively expensive chemical reaction, it is again our strong belief that we need to be keeping a very close eye on the reaction. And we see many different practices in the industry, from some pre-purification steps coupled with UV detection to no monitoring at all, in fact. But we've been working very hard on developing tools that could look again at the earliest time points of the reaction and resolve nascent RNA from the building blocks, because it's the NTPs that are being, if you want, stitched together into a chain. And so we want to know at any point in time of the reaction, what is the concentration of our building blocks, so that we can ensure that our reaction is proceeding seamlessly. If we run out of one building block, the whole chain elongation will stop. And so we developed this very rapid analytical method with the runtime, or I should say for clarity, the resolution time on the method is 3 minutes, which is relatively very short in the time scale of the reaction, which I said is between 2 to 3 hours. So in the space of 3 minutes, we can get information on the concentration of mRNA, which with this particular method oftentimes shows as 2 peaks, and we can talk about this in Q&A session. But this recovers all of the RNA present at any point in time in our IVT reaction. We can monitor, in fact, the concentration of the linearized plasmid that we put into the reaction, and we can monitor the concentration of individual NTPs and capping reagent that we put into the reaction. A lot of information in very short analytical time, which is why we call this a multi-parameter method, and it's, as far as I'm concerned, quite a new paradigm in the mRNA development world. But still have to juxtapose it against perhaps a more traditional one parameter at a time analytical approach, which would also deliver us useful information on the concentration, for example, of polyadenylated mRNA in our reaction. And this analytical approach would be akin to the protein A analytical column used for monoclonal antibody titration. So if you're a fan of this approach from the monoclonal antibody industry, then perhaps an analytical oligo DT column would be an interesting fit. But with this approach, you do not get all of the valuable information on the concentration of non-polyadenylated mRNA, as well as you don't get any information on concentration of plasmid, as well as nucleotides and capping reagent. So I'll be taking this approach forward and see how we can use it to make more RNA faster. First approach is to look at our most simplified batch IVT reaction, where we put into the reaction certain concentration of nucleotides, certain concentration of polymerase, certain concentration of plasmid, and we just see what goes on as a function of time. This is what you typically see. You started with some concentration of nucleotides, which slowly decrease. That depends on the relative amount of each nucleotide in the sequence. So this NTP mix was not very well optimized for the abundance of UTP, CTP, GTP, and ATP in the sequence. That can be sorted out in the optimization. And as the nucleotide peaks were decreasing, mRNA concentration was increasing. When the first nucleotide ran out, that's approximately when production of mRNA stalled. This nice Excel plot is actually just an integration of chromatographic peaks that we were recording in near real time. Like I mentioned earlier, after 3 minutes of injecting the sample, we knew already what's the concentration of RNA versus concentration of each nucleotide. This is a capping reagent. In this case, we used ARCA. We very often use CleanCap or other capping reagents that might be available. So this is the first step. We know how much material we get from a particular concentration of nucleotides. Of course, you can then take this a step further and start playing around with the reaction. And this is a non-exhaustive list of possible things that you can do with your reaction. It's a multi-component, approximately 13-component reaction. You can imagine you can vary each one either at once or in combination. But here I just give some examples of how we played around with the concentration of magnesium and looked at the effect on the rate of mRNA production, or we played with the concentration of nucleotides, or with the concentration of plasmid DNA in the reaction. We published this in the paper referenced below, and we were very proud also to get the front cover on biotechnology, bioengineering back in March this year, and I invite you to read this publication. Perhaps it gives some ideas about optimizing the reaction. But we don't claim that we have fully optimized the reaction. Rather, we would like to suggest there is high value in looking at the reaction in near real time by complementing mRNA concentration data with nucleotide consumption data, which gives a lot of insight, oftentimes over not detected, not recorded, and during the process of optimization. We can take this a step further. So with the use of the same analytical tool, we can then start optimizing for addition of nucleotides when those run out. This is a basic fed batch approach. So here we're looking at nucleotides being consumed, and at the point where the first nucleotide has reached about 10% starting value, we spike in more nucleotides. We don't want to oversaturate the system with nucleotides, as this might cause substrate inhibition, and we don't want it to run out. So that we need to be constantly looking for a steady state of nucleotide concentration. You could be adding other things into the reaction, for example, polymerase or plasmid and so forth. We were playing just with the most basic system of adding nucleotides and magnesium to increase the yields of IVT reaction. And so once you have optimized for a particular fed batch scenario, you could be thinking then about automating this. I describe here work published in a different publication, which I also invite you to read. The reference is given down here. This one was published in Chemie Engineered Technique end of last year, and it was about how to then automatize the production of mRNA based on the concept of fed batch. And it was using a single-use bioreactor called Ember 250, produced by Sartorius, which instead of us having to individually spike in nucleotide magnesium boluses, did it on our behalf in an automated fashion. First, as mentioned, we had to figure out the kinetics of the reaction for a particular mixture of plasmid polymerase concentration and starting NTP mix. So the kinetic curves here were very important. We also wanted to verify that the quality of RNA was constant throughout the run, and these are sometimes questions. Did we see an increase in double-stranded RNA formation, for example? No, as is shown here with J2 dot plots that were published. We don't actually see any significant or any increase at all in double-stranded formation, which somehow makes sense because we're not saturating the system with, but rather we're keeping the system in a nice steady state. And so the polymerase is constantly acting in a constant fashion. So these were, let's say, our starting conditions for starting feeding regime. So we calculated the feeding rates, and then we employed an Ember 250 to essentially do the feeding for us. At this point, we turned on the feeding based on calculated feeding rates, and came back a couple of hours later after the reactor has been feeding the reaction. And because the calculation was at least approximately right, we were actually able to keep the nucleotides in steady state for this duration, whilst the RNA was being constantly produced. We're looking here at the concentration of RNA in mg per mil, let's say. So this is 12 mg per mil at its maximum. It doesn't mean that there was no RNA produced in this intermediate phase, but as we were introducing more and more nucleotides, by feeding the reaction, we are of course also increasing the volume of the reaction. So if we just look at what we call transcription factor, meaning how much mRNA mass we produce, we would actually see a constant increase with time. And so from a standard 200 mass-to-mass transcriptions, we can easily take this up to 400 and more transcriptions, meaning we made 400 mass copies of mRNA for each one plasmid mass. And if we took molar equivalents, this would be even 3 times higher. And the quality of RNA throughout this many hours was also unchanged. So that was one approach towards making a lot of mRNA in relatively short space of time, and also in a small footprint that was greatly helped by the at-line monitoring based on HPLC using what we call the CIMac PrimaS analytical method. This work is published down here, and again, I invite you to read more if you're interested on this. And in the remainder of my time with you today, I would like to tell you a few snippets of our work in then purifying the mRNA out of the IVT mixture. We're chromatographers, so we believe in the power of chromatography to produce pure RNA, pure and stable RNA, I should say, in a scalable fashion. Most of the time, we like to use oligo-DT wherever possible, wherever we're dealing with polyadenylated mRNA, which is not always the case anymore in the RNA industry. In case where we're not dealing with polyadenylated RNA, we revert to multimodal ligands. Commercialized ligand is called PrimaS, and we are soon introducing something called Swiper. Stay tuned for this. And then, because we want to remove double-stranded RNA impurity in case it was produced in the IVT, we typically resort to either reverse phase or HIC condition for polishing. And I want to spend a few minutes to tell you more about those, at least those 3 first purifications. So oligo-DT, like I mentioned, this is the affinity ligand. It's like the protein A used for MABs. There is, I would say, not so much science to be discussed around this. We need to load the RNA at a particular increased salt concentration to achieve binding of RNA to the ligand, and polyadenylated mRNA binds to the DT ligand in a forming an AT base pair essentially, and everything that is not polyadenylated simply flows through the column, and we release then mRNA by decreasing the conductivity, by decreasing the salt concentration in our elution buffer. Quite often we simply employ water, which gives us then a lot of flexibility in the further downstream steps. We can spike in any salts that we want, or you can use low molarity citrate, for example, or any other low molarity buffer. What's certain interesting findings that we found over the years and are also published in the reference given here below is that monoliths, which are traditionally and typically found to be flow rate independent chromatographic media, show some flow rate dependence exclusively in the realm of oligo-DT chromatography. This is an interesting feature that I think deserves more academic interest. Basically, we have relatively short stretch of mRNA that has to find a relatively short stretch of the ligand on the column, and so we do want to give it a necessary residence time. And so we have shown that, for example, decreasing flow rate for loading from 1 to 5 to 10 column volumes, which is high flow rates by any given standard, can lead to a decrease in binding capacity. But we get very respectable binding capacities, even at 10 column volumes per minute, given here for the example of EGFP mRNA. If we work with 1 column volume per minute, which would be scale-up flow rate, also used typically for scale-up because of pump requirements for scale-up, then we can reach 4 to 5 milligram per milliliter binding capacities for a molecule like EGFP quite standardly. We work a lot with 96-well plates to screen binding and elution conditions. Here by the use of such 96-well plates, which don't actually require a chromatographic skid, but just a vacuum manifold, we found that, for example, switching from sodium chloride as the binding salt to guanidinium hydrochloride, which is a stronger chaotrope, we were actually able to drive the binding capacity by approximately another 30%. In case of EGFP, we were able to demonstrate even 6 milligram per milliliter binding capacity, which is the highest binding capacity currently known for mRNA as far as we're concerned. And we can sometimes use this concept of guanidinium instead of sodium chloride, especially if stronger binding needs to be achieved in certain contexts. However, we always also underline the fact that sodium chloride itself can lead to precipitation of mRNA, so this needs to be carefully optimized, and guanidinium, being a stronger chaotrope, can lead to precipitation even earlier. So this is a proviso that I need to say while talking about guanidinium. But for constructs which are not prone to precipitation, this can be quite an interesting process solution. We optimized this in a 96-well format, transferred it to a column scale-up format, and actually demonstrated that if we determine 6 mg per mil in a 96-well plate, we then demonstrate 5.5, so only 10% less binding capacity in a column format, meaning this is quite a nice scale-down model for oligo-DT. Another interesting feature that actually came as a bit of a surprise to us at the time, and still generates a lot of surprises when we present on this, is the fact that if you look at mRNA stability once purified through a relatively gentle purification strategy like oligo-DT, the mRNA, unless it contains some sort of auto-cleaving sites, is actually very stable. We were recently challenged by a reviewer who said, well, why do certain suppliers ship RNA frozen? Well, there are, of course, good shipment reasons for that, but actually any RNA that we've purified, we can more or less guarantee we can leave it at least on the bench for prolonged amounts of time if it's been purified, we say chromatographically, particularly by oligo-DT. Whereas precipitation methods that are typically used, especially at the beginnings of projects when quantities are small, we find that these tend to actually lead to relatively rapid degradation, particularly at slightly elevated temperatures. And we've heard now confirmation of this from multiple partners around the world, and you can try it for yourself and let me know the results later on. Arguably, this was done on EGFP, which is inherently a stable molecule, but we've demonstrated this also on Cas9, for example, which is 4,000 nucleotides, which was equally stable at 37 degrees for multiple weeks if purified by oligo-DT. If you'd like to read more, I give the reference here below to the paper published in Cell and Gene Therapy Insights a couple of years back. Right, to finish off, how about if the molecule of interest, RNA of interest, is not polyadenylated? Then we need to resort to non-oligo-DT strategies. And we've done a lot of work on a ligand, multimodal ligand combining properties of anion exchange and hydrogen bonding properties called PrimaS to produce mRNA in a scalable fashion by use of this ligand in combination with a pH gradient. and something that we call high salt wash. So high salt wash here going to 1 mole of sodium chloride washes off nucleotides and proteins and plasmid, and then a pH gradient elutes mRNA quite selectively. So this would be mRNA as separated from plasmid in this particular run. Very sharp eyes will spot that the pH required for elution from PrimaS is 10.5, which is relatively high for mRNA. And so we designed a rapid neutralization strategy. So we elute this RNA directly into potassium acetate buffer. And if we do so, then we're again able to demonstrate, this is shown here for EGFP, that for 1 week, even at 37 degrees, this RNA is very stable. We only start to pick up some degradation after nearly a month at 37 degrees. And molecule is very stable at room temperature for a month if purified using this multimodal approach. So this is quite a nice and robust solution for molecules not containing poly-A tail. And then I will finish off on question of polishing. A lot of time we get a question, how do I remove double-stranded RNA from my sample? And we've not come up with the concept of reverse phase chromatography to remove double-stranded RNA. There's a beautiful paper by Kathleen Caricot from many years back on the use of this. We're simply now validating this and showing it in a scalable fashion. This is a reverse phase chromatogram performed on an SDVB, which stands for styrene divinyl benzene monolith, used with acetonitrile and triethyl amino acetate, which very reproducibly and reliably separates out double-stranded RNA from single-stranded RNA. And quite often we see that short fragments and presumably some abortive double-stranded RNA fragments elute early in the gradient, and longer, presumably 3' extended double-stranded RNA sequences elute late in the gradient. And we see this time and again for construct after construct. And we can look at the purity of elution fractions also by a fragment analyzer, for example. And we quite often see that early fractions contain fragmented material and late fractions contain high molecular weight material, which oftentimes corresponds to 3' extensions. This is scalable up to 8 liter column volume, which can purify in the range of 10 gram of mRNA per batch. This is just another example showing much the same, but on a different molecule. In this case, it was done on the Cas9, so 4,000 nucleotide molecule. Again, we saw removal of 3' extended double-stranded RNA in the later part of the gradient, because longer double-stranded RNA is more hydrophobic than single-stranded RNA, taking into account our third physicochemical property mentioned at the beginning, which is hydrophobicity of RNA. I finish with this. In the interest of time, I will skip the take-home messages. I hope that I convince you that there is great value in combining analytical chromatography to support preparative chromatographic approaches to purify both plasmid and mRNA. If you have any questions, myself and the team would be delighted to take them either now or later on. And if I'm allowed, I would also like to invite you for a conference that we organize in Slovenia, by the Slovenian coast, in June 2024, where this science, as well as much other science dedicated to this, to purification of mRNA plasmids, as well as other interesting biopharmaceuticals, will be presented. I thank you for your kind attention, and I thank my beloved colleagues without whom none of these slides would exist. And I think we have a few minutes for questions.
Well, thank you very much, Rock, for an excellent presentation. We have indeed received a few questions already, but we will give the rest of you a moment to enter your questions in the question and answer box to the left of the slides. Before we do begin the Q&A, I'll run through some brief announcements. First, I'd like to thank Sartorius, BIA Separations, TriLink Biotechnologies, and Precision Nanosystems for sponsoring this digital week. Now let's get back to Rock to begin the Q&A. And I will start as I go through here. Let me just check in on the different questions we have received. And it looks like our first question is a calibration curve needed for quantification of RNA with PrimaS?
Yes, that's highly recommended. And in fact, absorption of RNA can be sequence dependent. So we actually recommend that you perform calibration curve for each analyte that you are analyzing. Yeah, so if you're making EGFP, it's recommended to perform calibration curve with purified EGFP mRNA for most accurate quantification.
Okay, our next question, and I'm going to start to roll through these a little bit just because we're just a little bit rolling through on time. So can fed batch IVT be continued indefinitely to reach higher RNA yield?
That's a very good question. I think the answer is no, but I would love to be proven wrong. And the reason is that feeding, of course, also dilutes the reaction. So unless we combine it with some kind of a volume reduction step, I think in the sense presented today, it cannot be continued indefinitely. But, you know, this is a fast evolving world. So here's a challenge to my colleagues.
Next one, we'll quickly roll through. Can CIMac PrimaS distinguish between capped and uncapped mRNA?
Not in the way as presented today, but we have developed an assay which makes use of exonuclease digestion that is selective for capped versus uncapped RNA. And so if we digest down the RNA with exonuclease, we're only left with capped RNA. And so by subtraction, we can work out what was the relative amount of capped mRNA. This is, in fact, published in one of the publications that I refer to, or reach out to me for more details later.
Another one from an attendee, is the UF/DF step recommended before the DEAE for pDNA purification?
We see, so it certainly helps with volume reduction of the feed. So we do see a lot of people using TFF beforehand. It is, on the other hand, an additional unit operation, additional systems required for that. So it really comes down to the fluid volume management strategy by each company. We don't always use it if we can handle the volumes that are processed then by the DEAE column.
Okay, well, there are a couple questions in there that we can certainly address after our presentation, but certainly that is all the time. We have 4 questions today after a terrific presentation from Rock, so thank you certainly, Rock, for a great session. If anyone did submit a question that wasn't addressed, do keep in mind that the speaker will reach out to you directly, and we'll definitely get in contact with you post-event. The session was recorded. You'll receive a notification in 24 hours when the on-demand session is available for viewing. Before you do log off, please take a moment to complete the feedback form so we can continue to improve your digital week experience. So on behalf of Informa Connect Life Sciences and the TIDES team, I'm Mike Moriarty, and have a great rest of your day.